Hi, welcome to the Signal Path. Today I'm going to do another product review for you guys. Now often on my channel I'm focused on very high-end instruments, sometimes costing more than $1 million. And this allows us to experiment and see what's the state of the art, especially during teardowns of these really high-end units. But that doesn't mean that more entry-level equipment is not interesting. In fact, because a lot of off-the-shelf components now have such high performance, you can put together fairly good equipment just using off-the-shelf devices. So we're going to take a look at that. Today, I'm going to review a synthesizer. Now, if you want to buy a synthesizer, let's say sub 6 gigahertz, there are so many of them available online. Now, high-end instruments like, for example, the Azure and EXG here offers vector modulation, very advanced and low phase noise, very spectrally pure, and a lot of functions built into it. So these guys are really pricey, intended for research and kind of industrial applications. So those are going to be beyond the budget for most people. But at the same time, if you look, there are a lot of USB-based synthesizers. Now, I often stay away from those because A, they have to be tethered to a computer. Their performance is not very good. They're not open source. You know, if you're going to buy something that's USB, you may as well have it open source. But recently, somebody sent me something which I think is going to be quite a bit of interest, and I'm going to take a look at it in detail and see how it performs. It's this little guy. This is a 12.5 megahertz to 6.2 gigahertz synthesizer, and not only is it, of course, USB based, but it has an LCD screen, which means it can run directly off of battery. So we're going to test it, look at its performance, and see what we can do with it. This is fully open source, which is even better. It is an Arduino based processor inside, or I should say Arduino compatible processor inside, so you can program it with the Arduino. The source code is available. We're going to take a look at all of that. So let's go and see how well this behaves. And here is the unit itself. This is by ERA Instruments, and this particular model is the ERASynth Micro. They do have an ERASynth Pro version and ERASynth Plus version, which go up to 20 gigahertz, and those are much higher performance. But this is their entry-level product that they just released. So we're going to focus on that, and hopefully we can cover the other ones at a later time. This one goes from 12.5 megahertz to 6.4 gigahertz, and naturally the very low frequency below 12.5 megahertz is not covered. And this is typical because of the part they're using to generate the output signal, which we can take a look at as well. So this is one limitation, that if you want to work below 12.5 megahertz, you can use this. But then at the same time, there are many low-cost synthesizers below 12.5 megahertz which you can use. This is intended for creating an RF signal, an RF carrier. Now here in the front, of course, there's the LCD, but there's also a connector here. This header can be used for you to directly inject the analog signals into it for modulation and other purposes, or you can program them to do pretty much anything you want from a digital I/O point of view, because you can program the processor. So this analog digital I/O port here can be quite useful if you're going to use it in the open source configuration and make modifications. We're going to try that as well. USB port here on the left, which is nothing surprising, USB micro, and then we have the RF output, and we also have the reference in and out, so you can either inject a 10 megahertz reference into it or sync this to something else by providing 10 megahertz at the output. So the exact architecture of how it's built inside, we will take a close look at as well. So let me turn it on. I'm going to just plug it into a USB power here. I have a battery here. And of course, as soon as you plug it in, it comes up almost instantly. So it's ready to use. And it's a nice little simple interface. You know, it comes with a little pen, which you can do. You can change all the different settings, and we'll take a look at all of those as well. The output amplitude and frequency can be directly set here. So as you can see, it's pretty nice and compact, and it is used immediately when you turn it on, which is a huge advantage. There's a couple of LEDs nicely built into here. You just got the power and the lock and the RF lock there. So I can, of course, turn this on. You can see the RF lock turns on. There's a heartbeat LED that shows you that the things are happening in the background. So looks very nice, pretty easy to use. As soon as you turn it on, nothing unusual going on. Now we should actually test it by hooking it up to some measurement equipment. So let's go ahead and take a look at the architecture of the ERASynth Micro. The full schematic is not available yet. This is a brand new product, but it will be. The code is, of course, is available. You can download it and take a look. So let's look at the architecture, because it tells us something about the limitation of the instrument, as well as how they perform some of the functions and capabilities of the unit itself. So let's start from the left over here. We have an SMA connector, which is our 10 megahertz reference in and output. This is a bidirectional port, and they accomplish this by using these triple buffers in this circular fashion. This is a common technique. By turning the buffers on and off in a particular order, you can either use this as an input or an output. Now they have a 10 megahertz TCXO. This is going to determine the absolute accuracy of the system in terms of frequency. This is not how the final phase noise of the system is determined. I'll talk about that in a little bit, but this is going to tell you how accurately your signal is going to be, let's say at 1 gigahertz. But of course, you're starting from 10 megahertz, which means that you're going to have to take the accuracy of the 10 megahertz and multiply it up in order to get the final offset. So if this is 10 parts per million, depending on the output frequency, you're going to have a certain offset. Now you also don't want to multiply 10 megahertz with a PLL all the way to 6.4 gigahertz. So they're going to be using a multi-stage PLL. This itself is a common technique in order to shape the phase noise characteristic of a system to the way you want it to be. So in this case, they're getting the 10 megahertz TCXO signal and they're putting it into an ADF4002. That is an analog devices phase detector synthesizer IC, which in then turn drives a 50 megahertz VCXO, a voltage controlled crystal oscillator. The difference between 10 megahertz and 50 megahertz may not seem like much, but that's a factor of 5. So that's 20 log of 5 of difference on the reference phase noise you're going to get. And this allows you to lock this 50 megahertz VCXO directly to the 10 megahertz TCXO and therefore drive the final synthesizer IC, which is an LMX2572, directly from the 50 megahertz signal instead. So let's take a look at the ADF4002. And this, you can see there's in a PLL loop. There you go, there's a PLL loop over here. And if we take a look at that IC, you can see there it is. It's an analog devices frequency synthesizer. This is a 400 megahertz part, but of course it's not used at 400 megahertz because you only have a 50 megahertz synthesizer. So there you go, you put your reference over here, that comes from a 10 megahertz TCXO, and you put your RF in here, and that's going to be the 50 megahertz VCXO. And you can configure it through a digital SPI interface and all the phase frequency detector and all the activities to compare and make sure the PLL is locked and everything is handled by these components over here. I'm going to make a separate video about PLLs hopefully later. I know I've been saying that for some time to tell you exactly how this works. And there's a charge pump here, and this charge pump is going to go all the way back over here and drive the 50 megahertz oscillator that is going to be on the board itself. So that takes care of the input portion, so that we are basically all the way up to here now. Now we have a 50 megahertz low phase noise frequency stable reference going into the LMX2572. This is now a full synthesizer with a built-in VCO. And if I go over here and take a look at its block diagram, you can see that it has a VCO over here, fairly wide range, and it's going to have dividers and charge pumps just like a normal PLL would. And we get our oscillator reference over here, and then there's a whole bunch of settings you can do, and ultimately the divider over here making a comparison and doing everything else. So again, very similar to a regular PLL. Now this is nice because it has a ramp generator and an FSK generator built into the chip itself. So you can do frequency shift keying and ramp directly in the IC, which is some of the functionalities that this synthesizer gives you because it's built into this IC that they're using, the LMX2572. By the way, this is from TI. And this has two outputs, both differential. You can see RF output A and RF output B. And RF output B in this case is not used. I wish they had actually used this and given you a second connector, SMA connector, because you can have the RF output B be a multiple of the frequency coming out of RF out A. As you can see, we have the programmable dividers here and a mux to select whether you have the main output, which would be this one, or the divided output coming over here. And because these are all independent, you could, let's say, have 1 gigahertz coming out of here, and then you can divide the 1 gigahertz by 4, 8, or 256 or whatever, and have a fraction of that coming out of here. That would have been quite a nice advantage, and I don't think it would have made the board that much larger, but it's sometimes nice to have fraction of the signal coming out of the synthesizer itself. So that really takes care of that part. And so now you have an output here. You can see the output B is not used. You have an output here which can go from 10 megahertz here, they say 10 megahertz, but they only tune it down to 12.5, all the way up to 6.4 gigahertz, which has FSK and ramp capabilities, but it doesn't have any amplitude modulation capability. So for that, they have an AM DAC followed by an attenuator, and they can produce a modulation directly on an RF attenuator and therefore give you AM modulation. The speed and the rate and the range in which this attenuation can be accomplished depends on the components used here, but we can take a look at that in the specification. And then there is two amplifiers going out. Now the nice thing about having this AM DAC here is that you don't necessarily have to use it for modulation. You can also use it for actual attenuation. So you can do an attenuation on this as well. To the best of my knowledge here, I think they're using this both for AM and for regular attenuation. You can see you can have a signal from -45 all the way to +15 dBm coming out of this. Now there's also a mic input and an external modulation input, which they put through some op-amp just for buffering it, and then that goes into the microcontroller ADC, which means that they digitize the external modulation signal going into it in order to be able to feed that directly into the LMX2572 from the microcontroller that's directly on the board. So it's a fairly straightforward architecture, two-stage PLL with some basic functionality built into it. I like the digitization of this and the triggering going to the MCU allows you to reprogram this and repurpose these pins, because now you have the ADCs in there, and do all kind of other things. You don't have to use it for this functionality. This is just what they have done based on the code they have written. It's fully open source, so we can modify it around. So there it is. That's how it works. Now we can actually go ahead, take a look inside the unit, because I want to show you what's in there, and then finally hook it up to some instrument and look at the signals. So let's go ahead and take a look and see what's inside this unit. I've already taken the screws off. Let's go ahead and separate them. And there it is. You can see there are two main boards in here. At the top, we have an external LCD screen with a touch screen built into it. This is a fully standalone unit. It makes sense for them to use something like this, because there's no reason to reinvent the wheel and design this from scratch yourself. This has a serial interface. You can draw your own GUI, get signals in and out. Basically, all the GUI design work is handled off to this board. This is actually really common. Even in most modern instruments, people don't want to remake this over and over again. You can just buy it off the shelf. Why not? And nicely, everything's tied down. There's some glue over there to make sure things don't separate. Glue on the cables, nice attention to details, making sure that things stay in place. So let me go ahead and zoom in on this main board, which we're going to talk about. Get this cable a little bit out of the way. There it is. Now, a lot of the components I just spoke about from the block diagram can be found directly here. One thing to keep in mind is that the only thing holding these SMAs to this main chassis is by the solder onto this board. On the other side of the board, there's quite a bit of solder, so I don't think this is going to come loose very easily. Nonetheless, you have to be careful putting torque on these SMA connectors, because there's no other way that they're attached to this whole chassis here. The chassis is plastic. Here's the IOs that I talked about, and the LEDs are over here, which can be seen through the chassis itself. So let's start from the left. Main processor. This is the Atmo processor that handles all the GUI communication, programming, all the calibration coefficients are handled by this guy over here. At the core is our main synthesizer. This is a 6.4 gigahertz synthesizer, which is using this 50 megahertz VCXO as its reference. This VCXO and this TCXO work in conjunction, as I explained. This guy is locked to this guy using this synthesizer function, synthesizer over here. This is the analog devices part. And you can see the proximity of this TCXO to the reference connector and the buffers around it to enable the bidirectional purpose of this SMA connector over here. So you can either inject your own 10 megahertz signal or use this one, lock this guy to this guy, and then this guy is going to use the 50 megahertz as a reference. The output of this, or one of the two outputs it has, the other one's just terminated, goes into this step attenuator. This is a digital attenuator, even though on the block diagram it doesn't show that there are two attenuators here, that in fact there are. One of them is digitally controlled by a main processor. This allows you to control the output signal level, so you can go from -50 to +15 dBm by using the digital attenuator. But the attenuator that follows after it is a voltage controlled attenuator, and this one is driven by a DAC, which allows you to do AM modulation. So they have decoupled those two functions, even though it's not shown there. And there's two amplifiers afterwards and an AC coupling directly to the output. So really quite nice and simple and elegant architecture over here. And the question remains, how well does it work? How well does the GUI work? What are the signals that the output look like? We can do some tests and then see how good it is around the lab. One minor thing I didn't mention, there's really nothing on the other side of the board except the vibration motor. This thing has a little vibration motor built into it that gives you haptic feedback when you push the buttons. It's okay. It's like a kind of like a phone, and when you press something, you know that you've pressed the buttons. It's nice. Sometimes it's useful to know that you've actually taken an action on the LCD screen. So let's look at the GUI and see how easy it is to use, and have a couple of suggestions which might be useful. Now, as I said, there's a vibration motor, so when I press this, I can feel haptic feedback, which is nice. Now, if you go under the frequency, you can see that the frequency is written on in hertz. Even though we have buttons for entering them in megahertz, kilohertz, and gigahertz, there is no decimal point here. So I can't go 1.1 gigahertz. I'm going to have to actually type it all the way out, even though I can do 1 gigahertz, and then it would enter it, of course. The other thing is that once I come into this menu, as soon as I start typing, it should clear this out and allow me to type and overwrite it. This is how normally instruments operate, but instead I have to clear it and do it one at a time, so which is a little bit of an annoyance. Same thing if you go under the amplitude, there is no decimal point. Now this may be a limitation on the fact that they want you to go in 1 dB steps, but as far as I know, that step attenuator supports 0.25 dB steps, so you should be able to, in theory, go by 0.25 dB steps. And this should here have a plus and minus sign, so you can just go plus, 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 minus, minus, minus directly over here, even though it's actually available over here, as you can see. So other than that, there is really not much annoyance Under the diagnostics menu, you can see that the different things are locked. You can see the temperature inside, and you can also see how much power is drawing, 1.3 watts or so. And if I turn it down, it will go up to about 2 watts. If I enable the output over here and I go into the diagnostic, you can see it's burning about 2 watts, which is pretty good. And which means that with an external battery, this thing is going to last a very long time, which is how I'm running it right now. You can do sweep generation, and we'll take a look at that because I have an experiment I want to show you with that. And then you can do modulation, which you can do AM, FM, and pulse, and drive the modulation either with an internal modulation source or with an external modulation source, as you saw with the input, either from the microphone input or the external modulation input. So it's nice, it's very simple, and again, you don't have to do much to be able to get some basic synthesizer functionality, which is nice. There's also a help menu which shows you all the connectors here, which is important because this text written here is tiny. It's very, very hard to read. It would benefit from having some cover that shows you the letters, kind of a surface finish, but I can imagine that would add quite a bit to the cost of making the case. That's probably why they haven't done it. So let's go ahead and take a look at a 1 gigahertz signal on the spectrum analyzer. So I'm going to go and turn it on, and there is our 1 gigahertz signal. Now you may ask, what is happening with all these other tones? So there's multiple things happening here which is worth mentioning. First of all, this tone that you see here on the left, if I can find my mouse here, there it is. This tone that you see here on the left, that's not from the instrument. Well, it's not exactly from the instrument. That's actually from my wireless microphone. But you can see when I turn the instrument on and off, the amplitude of the signal changes drastically. And that's because this board inside the synthesizer is not fully shielded, which means that traces that are on the board act as antennas, and they pick up the signal from my wireless microphone, which is operating around 512 megahertz. The problem is that those signals are picked up both before and after the amplifier that's on the board. And because we enable the amplifier when the output is enabled, the signal gets significantly amplified. So this board can definitely benefit from being better shielded so that you don't allow these signals being picked up and amplified normally. Remember, the amplifiers that are at the end of the chain just before the SMA connector are broadband. They work from essentially DC all the way to 6.5 gigahertz. So they're going to amplify anything that's picked up from the board. So this lack of shielding can cause some problem in some scenarios, or maybe not, depending on what you're doing. Now, the signal coming from my microphone is really close to this board. So, it's only, let's say, half a meter away. So yes, it's going to be picked up pretty strongly. So I'm going to move it a little bit further away as much as I can, and I can kind of rotate it around to create a null in the channel as much as possible so that we don't get that signal. So you have to ignore this. This is not from the synthesizer itself. And you may be able to shield this yourself by putting some copper tape on the inside. And I might actually try that and see if I can shield some of it and better and improve the performance of the synthesizer, because I really like this unit. There it is. So here's our signal of 1 gigahertz. Now we have also a second and third harmonic, of course. That's normal. And a lot of times this is not an issue for what you're working on. If you need a really spectrally pure signal, then maybe it's an issue. But at lower frequencies, this problem is of course worse. So let me go ahead and change this. Let's try 250 megahertz. So that's a much lower frequency. There it is. You can see all the different harmonics going around. Again, ignore the 512 megahertz signal. But yeah, it looks nice. This is normal for a synthesizer to have this. The really expensive synthesizers are going to be much more spectrally pure than this. But at higher frequencies, this problem is getting better, of course. So let's try, let's say, a 4 gigahertz signal. There it is. There's a 4 gigahertz signal. You can see it's harmonic. There's going to be more harmonics after, but I'm not showing it because it's stopping here at 10 gigahertz. But there it is. There's the amplitude. I can do another peak search over here. And where is the peak search? There it is. Yeah, looks good. 4 gigahertz, minus 1 dBm. It's set to 0 dBm. There's some loss in the cable. Everything looks very good. So no complaints here. That this signal here again goes up and down depending on how I move my hand, because I'm blocking the signal arriving at the synthesizer. Looking good. Let's go back to 1 gigahertz and do a phase noise measurement directly on this. I'm going to go under here. I'm going to change that to phase noise. And there it is. Here's our phase noise plot. Now you got to be a little bit careful with this, because the phase noise of this synthesizer is quite good. In some places it actually competes with the phase noise inherent to this MXA. So I can't even measure the phase noise of the synthesizer in some offset. But these numbers that you get here at let's say a 1 megahertz offset about minus 133, at a 1 kilohertz offset minus 102, these are actually the numbers that they report as well. So that's very competitive and really close to the phase noise of the MXA. So I'm quite happy with that. I think it meets its specs. I've tried different things and I've looked around the harmonics and everything. I'm not going to bore you with those measurements because they work. That's not really that exciting to show. It's more exciting to look at some of the other capabilities like the modulation and so on that's built into it. So let me set up a new experiment and see if we can use some of these modulations to perform some experiments. So I put an RF absorber here on the board. Let's give it a try and to see if this improved anything. So here is the transmitter put at exactly the same distance. You can see now we can't even see the tone when the output is disabled. Before we could see it. And when I enable the output, the amplitude is quite a bit smaller than it used to be. It's improved by about almost 20 dB or so from where it used to be. So I think that's a good improvement. I'm sure that's something that they can easily add. So let's take a look at some of the modulation capabilities. So under AM modulation, we can choose a few different modulation formats. Now, using a triangular modulation allows us to see the linearity of the system with respect to AM performance itself. So let's see here, I have a kilohertz modulation frequency, 99% modulation depth, that's the maximum we can get. And here at a 1 kilohertz, this is fairly slow. So we can see how well the triangular wave is being modulated. And then we can go at much higher frequencies up to 20 kilohertz, which is the maximum. And then we can see some of the limitations at those higher modulation frequencies. So here I'm going to use the Tektronix MSO5 series to take a look at the signal here. Because it has spectrum view capabilities, it allows me to do real-time spectrum analysis directly on the waveform. I've done a full video on that I encourage you to watch. It's a pretty interesting feature there. So having said that, here we go at the top, you can see the spectrum. It's a 1 gigahertz tone, and you can see there's a little bit of phase noise characteristic is present there. We've looked at that on the spectrum analyzer already, so nothing surprising there. At the bottom is a time view. Now I'm doing 3.125 gigasample per second, and I'm capturing about 3 milliseconds or so. That's 12.5 million points. So there's a lot of data being captured here because I'm interested to see the slow trend, the slow behavior of AM modulation here. So right now at 1 kilohertz AM modulation, I'm going to turn that on and see what we look at. And there it is. It's nice. It's a reasonably triangular shape. You can see it's got roughly equal rise and fall time. So it's a fairly clean AM modulation at 1 kilohertz. That's what you would expect to see. And its extinction is not quite as much as I want to see, but some of this is actually the noise of the instrument itself. So it's not the fault of the synthesizer. So let's go back and actually change the AM modulation frequency from 1 kilohertz to 10 kilohertz, which is 10 times as much. And let's see what happens then. There it is. That's 10 kilohertz. Now I can zoom in a little bit more, and you can see some of the imperfections of the signal beginning to show up. We have some steps in the response there. We have some glitches that occasionally appear. So you can see sometimes the width of the signal is longer, the width of the AM modulation is longer, and there's an additional step that gets introduced occasionally. I believe this is just a calibration coefficient issues and the DAC waveform that's being applied to the attenuator that's a problematic. I think this can probably be solved with a better calibrated filter coefficients and a better calibrated waveform directly from the DAC being fed to the attenuator. I think this is possible to do, but something worthwhile to check. And this, if you're very sensitive about the kind of modulation you get and the timing is very critical for you, this might cause a tiny bit of problem. But I think, again, being open source, you can look at the table, and I'm sure there are ways to accommodate for that so that these problems, this cyclical kind of skipping doesn't happen. But what I am also very interested in is the sweep behavior. Because this instrument can do a full sweep across a wide range of frequencies, I want to see how it does step-by-step sweep. Because we can use that in conjunction with a spectrum analyzer to get AC characteristics and see some scalar characteristics, some cables and filters and so on, which would also be useful. So let's go ahead and take a look at that. So first I'm going to do a really basic sweep from 950 megahertz to 1050 megahertz, so a 100 megahertz span, and I'm going to do that at 10 megahertz steps. The dwell time, the minimum dwell time the instrument supports is 1 millisecond, which means that you cannot jump between frequencies in less than 1 millisecond. That has to do with how long it takes for the synthesizer to be set up and engaging into a new frequency. So let's go and turn it on and see what that looks like. There we go. I'm going to start that. So right now we're going to be able to see the activity of the whole synthesizer in time. There it is. You can see bursts of outputs and bursts of silence in between them. And there's some interesting pulses that appear. And these pulses are generally undesired, and they're probably happening because the output PAs are being enabled and disabled, and there's some basically pulse leaks through because of that. And I can go ahead and zoom into one of them so you can see what it looks like. There you go. You can see there's a little spurious pulse there, which you obviously don't want to have. So let's go back and zoom out again so we can see the individual pulses. Again, keep in mind that I am capturing a ton of data here. So the instrument is performing quite well considering how much information is being displayed and processed. So let's do a single capture. So we can get a single point and fill the memory, and then it doesn't have to capture anymore. And I can look at the frequency at each of these bursts. So let's start from, let's say, this one. What frequency is that? So that is this frequency, so 970 megahertz, which means that the next burst has to be 10 megahertz higher. Let's go here. Let me see, it should be 980. There it is, 980 megahertz. And the burst after that should be another 10 megahertz higher. It should be 990. There it is. So you can see it is doing exactly what you would expect it to do. It means that because you only have 1 millisecond, the distance between these 2 points here is only 1 millisecond. So the instrument basically disables the output of the PA, disables the synthesizer, configures the synthesizer for the next frequency, and then enables it, allowing the next burst to be present. This is the shortest time you can do it so that you can get some meaningful signal coming out. Now, ideally, what you would want is a continuous signal that has no gaps in the middle, but that is not possible with this kind of synthesizer because the Texas Instrument unit requires you to basically wait for the synthesizer to achieve lock again and then frequency to stabilize. This is normal for a synthesizer. This is one of the ways you can produce basically an inexpensive sweep is by doing it this way. Overall, I have to say I'm fairly happy with it. It works reasonably well. I can go to another frequency. You can see it indeed goes up by 10 megahertz each time. And we can even study, how the frequency sweep actually happens and how each of the points begins and starts. And we can look at all of that. I'm not going to go into the details because you can kind of understand the limitation and the advantages of building a synthesized sweep this way. So now let's see if we can use this feature and somehow measure the response of a filter, because we should be able to synchronize a spectrum analyzer and this unit simultaneously because the timing is very well known. So we could inherently lock them together. So let's try another type of modulation here. As I explained earlier, this unit accepts an external modulation input, so you can input an analog waveform and create a modulation directly on the AM or the FM inputs of this instrument. So right now I have it connected to the modulation port, FM modulation, and that signal is simply coming from any arbitrary function generator or synthesizer. It doesn't matter. This is a low frequency signal just to produce an FM deviation. Now we can go ahead and put that signal directly into our spectrum analyzer and do full analysis on it and do an AM demodulation or FM demodulation and figure out how it performs. So let's take a look. So let's look at the demodulated signal here. It is important to appreciate what it is we are looking at here. If you recall, I'm applying an analog waveform to the synthesizer. This analog waveform right now is a 100 Hertz sinusoidal input directly to the modulation input, meaning that we're going to get some FM modulation at a particular depth but at a rate of 100 Hertz. So I'm using this instrument to demodulate that. Now any imperfection we see from the demodulation is going to be coming from the synthesizer. So what we want here to see is the exact replica of the function generator input to the modulation of the synthesizer itself. So we can analyze the imperfection of the synthesizer through the process of FM modulation. So let's take a look and see what we get here. So let's look at the spectrum. Here is our 2 gigahertz center frequency. The span here is 50 kilohertz. So you can indeed see that there is some FM modulation. And this FM modulation width is about 25 kilohertz, which is exactly what it should be. Now the question is, how does the waveform of the demodulated signal actually look like? Because it should be a perfect sinusoid at 100 hertz. So I can go back out and look at the waveform here, and there it is. It looks fairly nice. And if you look, you can see some steps in there. And those steps are because, if you remember from the block diagram, the synthesizer first digitizes the input using an ADC before applying it to the Texas Instrument modulation port of the synthesizer. So there's going to be some quantization noise there. That quantization noise is undesired, but it looks like it's an 8-bit synthesizer, so 8-bit ADC. So it's not really that big of a deal. It's going to be some quantization noise, but this linearity looks fairly good. And we can verify that by looking at the demodulation parameters. Here we go. You can see that the demodulation rate is 100 hertz, as to be expected. We can see that we have plus and minus about 12.5 kilohertz of modulation depth. That's also exactly right. That's what it should be. And if you look at the THD, it's 0.25%, which is very good. It's doing a good replication of the FM modulation when it's being demodulated. So it's a pretty good modulation performance here. But I should be able to do this modulation up to 2 kilohertz. So let's go ahead and increase the input from 100 hertz to 1 kilohertz, which is 10 times more. There we go. So now I expect the modulation to be 10 times faster. So let's go over here and look at the waveform at a much smaller span here. As you can see, it's no longer sinusoidal. This is most likely because the ADC that's used is undersampled, so it doesn't get a lot of samples from our sinusoid. As a result, you're going to get very poor performance from in between the steps. You're going to have, of course, this sinusoidish looking thing, but it's not going to be very good. So what is the implication of that? Well, you're going to still get the FM modulation depth you're looking for. If I go back over here and look at the performance here, let me restart that. You can see that the modulation depth is indeed still 1 kilohertz, and you can see the modulation rate is 1 kilohertz, and the deviation is about 12.5. So you're getting that performance. But now the THD is quite a bit worse. It's now 5%, which is a lot worse, and that's about 20 times. And that's to be expected because we don't have a good sinusoid performance, but depends on how critical your application is. If your application is not super critical, then it doesn't really matter so much. But it is good to know the limitations of this, and this again comes from the fact that you have that ADC and then you have to sample that ADC. But having that digitization in the front gives you a lot of other capabilities, which means you can write your own functions built into the unit itself and create every kind of modulation that you want. You're not limited to what's built into the unit. You have full digital control over that. You basically can build your own little arbitrary waveform generator inside using a digital code, which is quite powerful. So nonetheless, I think it's good performance. Now, because this instrument supports the sweep across this entire frequency range, we could use it to measure the characteristics of active or passive devices. Now, this one right now is connected to a bandpass tunable filter, and the filter is set to 2 gigahertz. There's a couple of ways you can go about doing this. Because it supports a trigger input and output, you could in theory create a trigger point and then synchronize this with the spectrum analyzer sweep precisely so you can measure at the beginning of a trigger signal. But even that is not really necessary. You can just basically look at an infinite trace on a spectrum analyzer and do a persistent hold to look at the waveform. So we're going to look at that. The output of this is directly connected to the input of the filter, and the output of the filter then goes directly to the spectrum analyzer. So we can look at the screen and look at the filter response. Okay, let's take a look and see what happens here. So first I'm going to go under trace and I'm going to do max hold. So now we're just going to hold the trace on the screen. And I'm going to enable the sweep. Here's the sweep. Now we wait for it to be built up. There it is. So we can see where the filter is actually centered. I'm going to wait for this waveform to reach to the end of the screen. It's there at the bottom. You just can't see it. And then it's going to go, and then there should be some more. There it is. There we go. Looks nice. So we go under the marker now. If I go to 1.5 gigahertz for the marker, that's precisely the middle of the band. That is exactly where the filter is set to, 1.5 gigahertz. But we also see some interesting artifacts over there. We see that the filter also has some response at significantly higher frequencies at about 3.5 gigahertz. And this is normal for cavity filters because we're looking at such a wide frequency range, much larger than the percentage bandwidth of the filter itself. You're going to have other resonances show up in the filter's bandpass, and which is of course undesired. Even though this is supposed to reject everything outside of 1.5 gigahertz, we can see that it is indeed not the case. Even though if I look over here, you can see this, the value here is minus 20. So it's got 20 dB rejection at the second null here, or I should say in the second bandpass here. But anyway, that's not as good as you would want it. You want this to go down to minus infinity, of course. But that's normal. This is to be expected from a cavity filter. But you can see that you can these properties of the filter can be measured directly from the synthesizer itself because it has such a wide tuning range, and we can do a sweep directly on it. You don't need any other instrument. As you can see, I can measure this directly with the spectrum analyzer. And if you're using an oscilloscope that has enough bandwidth, you can also do it with an FFT as well, and it's all really the same. But you can see a nice scalar measurement here. And there you have it. I hope you enjoyed this quick review of this unit. Again, for $200 with all the features and built-in LCD screen and open source schematic and code that's available, I'd say it's pretty much a no-brainer. If you want to do anything in these frequency ranges, it's a very nice little device. It would be a nice addition to the lab. I'm sure I can find quite a bit of use for it just from its portability alone here around the lab. So anyway, let me know in the comment section what you think about it. I'm going to also see if I can get the higher frequency versions of these because I have some cool plans for them. We might be able to build some pretty neat stuff using their higher frequency synthesizers as well. Anyway, I'll see you in the comment section.